Good morning, everyone. Thank you for joining us today. Welcome to the Deep Dive. In our last deep dive, we journeyed beyond the desktop, looking into mobile and embedded architectures. Today, though, we're casting our eyes a bit further towards the really big horizon, the future of computing hardware. Breaking barriers. Our mission here really is to unpack these huge shifts that are happening in computer architecture. As we move beyond the old limits, the things that defined computing for so long, we're definitely moving from that predictable scaling era, Moore's law, into something, newer, more diverse, more creative in hardware design. And to help us navigate all of this, which is, let's face it, pretty complex, but also super exciting, we have our expert with us, someone with really adaptable expertise across computer science, AI, and computer networks.
Hello, everyone. Thank you for having me. It's a great pleasure to be here to discuss this important topic.
It's fantastic to have you. Now, for you listening, maybe you're prepping for a big meeting or just trying to get up to speed on the field, or maybe you're just really curious about what's next in tech. This deep dive is absolutely for you. We're aiming for those, aha moments, trying to make these pretty complex ideas feel, accessible. So to do that, we've set up our chat around some key questions. We'll kick things off with the basics, the context, what's going on with Moore's Law. Then we'll dig into the new chip designs popping up, things like 3D stacking and chiplets. After that, we'll look at the explosion in specialized hardware, think AI, quantum computing, and then touch on something really crucial, sustainable IT. And finally, we'll wrap up by looking at how edge and cloud computing are evolving together, because that dictates where all this cool new hardware actually ends up living. So let's dive in. Okay, first things first. Moore's Law. It's a name everyone recognizes, right? For decades, it was like the clockwork of the industry driving things forward. But now, it feels like it's slowing down. What exactly is Moore's Law, and why all this talk about it ending?
Right. So Moore's Law, it really goes back to Gordon Moore, the co-founder of Intel, back in 1965.
65, wow. That's a long time ago in tech years.
It really is. And his observation, or maybe prediction, was that the number of transistors you could cram onto an integrated circuit would roughly double every 2 years.
Doubling every 2 years. That sounds intense.
It was, and it became more than just an observation. It turned into this kind of self-fulfilling prophecy for the whole semiconductor industry. For a remarkably long time, this exponential growth really did hold up, and the main driver was our ability to just keep shrinking transistors smaller and smaller. That's what we call process node scaling.
Okay, scaling the process nodes.
Exactly, and that's what gave us, faster, cheaper, more power-efficient electronics generation after generation. But that predictable march is now running smack into what some people call the unyielding wall of fundamental physics.
Unyielding wall of fundamental physics. Okay, that sounds serious. What are these actual physical barriers? What's stopping us from just making transistors tinier and tinier forever?
Well, there are really two main physical limits we're hitting hard now, especially as transistors get down to the, single-digit nanometer scale.
Okay.
First, there's something called quantum tunneling. At these incredibly small sizes, quantum mechanics starts to play tricks on us.
Quantum mechanics, right?
Yeah, electrons can essentially tunnel right through the insulating gate of a transistor, even when it's supposed to be switched off.
So they leak through.
Exactly. It causes leakage current, which leads to errors. And maybe even more critically, it generates a lot of wasted heat. It's like a faucet that just won't turn off completely, always dripping.
Okay, that makes sense. What's the second barrier?
The second major one is the heat density problem, sometimes called the power wall.
Power wall.
Yeah. When you pack more and more and more transistors into the same tiny area of silicon, the amount of heat they generate per square millimeter just goes through the roof. It becomes astronomical.
Right, because they're all generating heat in one small spot.
Precisely.
Yeah.
And we're hitting a point where it's becoming physically impossible to pull that heat away fast enough to stop the chip from, literally overheating and failing. Imagine trying to cool a microscopic furnace. It's incredibly difficult.
So fundamental physics limits. But I imagine there are economic factors tangled up in this too, right? It can't just be about the science, what's happening on the money side of things.
Oh, absolutely. The economics are, in some ways, just as big a wall as the physics. First off, the cost of building these state-of-the-art chip factories, the fabs.
Yeah, the fab.
They've just skyrocketed. We're talking tens of billions of dollars, billions with a B, for one single facility.
Wow, so only a few companies can even play that game.
Exactly. It concentrates manufacturing power hugely. And then second, there's the complexity. Making these incredibly advanced chips is just mind-bogglingly complex. And because it's so complex, the manufacturing yields, the percentage of chips that actually work correctly, tend to be lower, especially early on.
Okay, so it's harder to make them work.
Right. And the combination of that massive fab cost and the lower yields means that the cost per transistor isn't really dropping like it used to.
Ah, so that famous trend of things getting cheaper as they get smaller.
That's basically stalling out. This is related to something called the end of Dennard scaling. For decades, smaller transistors also used less power proportionally, so the cost per computation kept falling. That was the real free lunch.
And the free lunch is over?
Pretty much, each tiny step forward now costs a lot more money.
Okay, so the era of just shrinking things to get faster and cheaper seems to be winding down. The free lunch, as you said, is over. So if shrinking isn't the main path forward anymore, what are engineers doing instead? What are the new strategies?
That's the crucial question, right? And the industry has really had to pivot. We're seeing, I'd say, three main strategies emerge.
Okay, what are they?
First, there's a huge focus on just designing smarter architectures. Instead of just more transistors, make the transistors you have work smarter.
Smarter how?
Things like designing CPU cores to execute more instructions per cycle, that's IPC, getting more work done each clock tick. And, really importantly, creating specialized hardware accelerators. Chips designed just for one specific job.
Right, like graphics cards or AI chips.
Exactly. It's about optimizing for the task, not just general speed. The second strategy is parallelism.
More cores.
Yep. Simply putting more processing cores onto a single chip so it can tackle more parts of a problem simultaneously. We've been doing this for a while, but it's becoming even more central.
Okay, smarter cores, more cores. What's the third?
The third one is kind of fascinating, moving into the third dimension.
Third dimension, like stacking things.
Precisely. Instead of just spreading things out wider on a flat piece of silicon, engineers are figuring out how to build chips taller, stacking components vertically.
Stacking chips on top of each other.
Yes, creating denser, potentially more efficient designs by using that vertical space.
Interesting. Okay, let's dig into one of those smarter architectures you mentioned, chiplets. What exactly is a chiplet, and how does that whole idea change how chips are actually made, especially compared to those big single-piece chips?
Right. Chiplets are a really big deal. So traditionally, if you wanted a powerful processor, you design this one massive single piece of silicon, a monolithic die, that had everything on it. All the cores, the cache, the I/O, everything.
The whole shebang on one chip.
Exactly. But the problem is, the bigger that single piece of silicon, the higher the chance there's a tiny defect somewhere on it. Even one microscopic flaw could ruin the entire chip.
Ah, so lower yields, higher costs.
Bingo. Especially as chips got bigger and more complex, yields could become a serious headache, making those huge monolithic chips incredibly expensive to make reliably.
So how do chiplets fix that?
The chiplet design philosophy flips that on its head. Instead of one giant die, you build the processor out of multiple smaller, often specialized dies called chiplets. Think of it like building with high-tech Lego bricks.
Okay, smaller pieces.
Smaller pieces. And AMD really kind of brought this into the mainstream consumer space with their Ryzen CPUs.
Right, I remember the buzz around that. How do they do it?
Well, for example, a Ryzen CPU might have one or two chiplets called Core Complex Dies, or CCDs. These contain the actual high-performance CPU cores.
Okay, the main processing units.
Right, and they manufacture these chiplets using the absolute latest, most advanced, and therefore most expensive manufacturing process to get the best performance.
Got it.
But then, these CCDs are connected on the package to a separate chiplet, the I/O die.
And what does the IOA do?
It handles things like the memory controller, PCIe lanes, USB connections, all the input-output stuff. And here's the clever part. They can make that I/O die using an older, more mature, and significantly cheaper manufacturing process because it doesn't need the absolute bleeding-edge speed.
So you mix and match the manufacturing tech based on what each part needs.
Exactly. It's a much more flexible and economically sensible approach.
That makes a lot of sense just from a manufacturing point of view. But what about the user? What are the main benefits for performance and cost with this chiplet approach? Are there any downsides?
Yeah. The benefits really stack up. First, as we touched on, improved yields and lower costs. Making several small chiplets is just way more cost-effective than trying to get one giant perfect chip. Fewer defects per chiplet means more working processors overall.
Right, less waste.
Less waste, lower costs per functional unit. Second, it offers fantastic modularity and scalability. Need a server chip with tons of cores? Just add more core chiplets, CCDs, to the package. It's much easier to scale up or down.
Like building bigger Lego models.
Kinda, yeah. And third, there's that flexibility we just talked about. Mixing and matching different process technologies lets you optimize for both cost and performance in a way that's really hard with a monolithic design. You put the expensive tech where it counts most.
Okay, those are some strong advantages. What about the trade-offs, though? Is there a catch?
The main challenge really is communication between the chiplets. Moving data from one chiplet to another across the package, interconnects like AMD's Infinity Fabric, is inherently a bit slower and uses a bit more power than moving data within a single piece of silicon.
So there's some overhead there.
There is. Engineers spend a lot of time optimizing those interconnects to minimize the latency and power cost, but it's an inherent trade-off compared to a perfect monolithic die. It's a balancing act.
Okay, that makes sense. Now, you also mentioned moving into the third dimension. Let's circle back to that. What exactly is 3D chip stacking, and what's the primary win? Also, doesn't stacking things just make that heat problem we talked about even worse?
Right. 3D stacking, it's literally what it sounds like. Layering multiple silicon dies, one on top of the other.
Like a silicon skyscraper.
Exactly. And these layers aren't just sitting there. They're connected vertically by thousands upon thousands of tiny microscopic electrical wires called through-silicon vias, or TSVs. Think of them as tiny elevators carrying data between the floors of the chip stack.
Thousands of vertical wires.
Yeah.
Okay, so what's the big advantage of doing that?
The primary benefit is dramatically reducing the distance data has to travel. Instead of signals potentially having to snake all the way across a wide, flat chip,
They just go straight up or down?
precisely, a much shorter path.
And shorter paths mean faster communication, less energy.
Both. That shorter distance translates directly into several key advantages. First, massively increased bandwidth. Because you can have so many of these vertical TSV connections packed closely together, you create this incredibly wide data highway between the layers, much wider than you could typically achieve horizontally.
Okay, more bandwidth. What else?
Second, lower latency. Shorter distance equals faster travel time for the data. Signals get where they need to go quicker.
Faster is always good.
And third, improved power efficiency. Driving signals over those microscopic vertical TSVs consumes significantly less energy than driving them across long horizontal wires on a traditional chip.
Right, less distance, less power needed.
Exactly. So more bandwidth, lower latency, better power efficiency. It's a compelling combination.
Can you give some real-world examples? Where are we seeing this used?
Sure. One of the most prominent examples is high bandwidth memory, or HBM. You see this a lot on high-end graphics cards and AI accelerators. They actually stack multiple DRAM memory dies right on top of each other, often on the same package as the main processor.
Stacking the memory right next to the processor.
Yeah, connected by TSVs, it provides absolutely enormous memory bandwidth, which is crucial for those workloads. Another great example is AMD's 3D V-cache.
Ah, yeah, I've heard about that for gaming.
Right. They stack an extra die of L3 cache memory directly on top of the main CPU cores. That extra, very close cache gives a significant performance boost in many games that are sensitive to cache size and latency.
Okay, so it's definitely happening. But what about the heat? You stack these hot components. Doesn't that create a thermal nightmare?
You've absolutely hit on the main challenge. Yes, stacking heat-generating layers definitely intensifies the thermal density problem. It makes it harder to get the heat out.
So how do they deal with it?
It requires really innovative cooling solutions. Engineers are working on things like microfluidic channels within the silicon stack to carry coolant, using advanced thermal interface materials between the layers, and just being very strategic about which components get stacked to manage the heat flow. It's a huge area of ongoing research and engineering.
So it's a challenge, but the performance benefits make it worth tackling for certain applications.
Exactly. It's not a universal solution for everything yet. But for things like HBM or V-cache, the payoff is significant enough to justify tackling the thermal complexity.
Okay, fascinating stuff. Now, moving beyond these sort of general purpose improvements, you mentioned an explosion of specialized hardware. Let's talk about AI first, as it's driving so much innovation. What is neuromorphic computing? It sounds different.
It is very different. Neuromorphic computing is a really radical departure from the standard computer architecture we've used for decades, the von Neumann architecture, where you have separate processing and memory units.
Okay, so it breaks that model.
Completely. Neuromorphic chips are designed to mimic the structure and function of the biological brain. They contain networks of artificial neurons and artificial synapses.
Neurons and synapses on a chip.
Essentially, yes. And the key difference is how they process information. A traditional chip runs on a clock, processing data step by step, cycle by cycle, whether there's new information or not.
Right, the constant clock tick.
A neuromorphic chip, however, is event-driven. The artificial neurons only fire, meaning they activate and consume power when they receive a significant input signal from other neurons, much like how neurons in our brain work.
So they only work when there's actually something to process.
Exactly. If there's no new input or event, they sit mostly idle, consuming very little power. This event-driven nature makes them potentially thousands of times more power efficient than traditional chips for certain types of tasks.
Like what kind of tasks?
They're particularly well-suited for AI tasks involving real-time processing of sensory data like vision or audio recognition or pattern matching. Anything where the system needs to react quickly to changes or events in the input rather than constantly crunching numbers. The power savings could be enormous for edge devices or continuous monitoring systems.
Wow, thousands of times more efficient. That's incredible. Okay, another area that sounds almost sci-fi is quantum computing. Can you break that down for us, starting with the absolute basics? What is a qubit?
Right, quantum computing, it definitely has that sci-fi feel. First thing to understand, it's not aiming to replace your laptop or smartphone. Classical computers will still be essential for most things.
Okay, so it's not a replacement.
No, quantum computers are a completely different kind of machine, designed to tackle a specific class of problems that are basically impossible and tractable for even the most powerful classical supercomputers we can imagine.
Problems beyond classical reach. Got it. So the qubit.
The qubit is the fundamental building block, analogous to the classical bit, but where a classical bit can only be a 0 or a 1.
A qubit can be both.
Kind of. It can exist in a state called superposition, which means it represents a combination of both 0 and 1 simultaneously. It's like a spinning coin before it lands. It's neither heads nor tails, but a probabilistic mix of both.
Okay, superposition.
Yeah.
That's already bending my brain a bit.
It gets weirder. Multiple qubits can also be linked together through a phenomenon called entanglement.
Entanglement.
Yeah, entangled qubits have their fates intertwined. If you measure the state of one, you instantly know the state of the other, no matter how far apart they are. Einstein famously called it spooky action at a distance.
Spooky indeed. So how does superposition and entanglement let quantum computers do things classical ones can't?
By leveraging these quantum properties, a quantum computer can essentially explore a vast number of possibilities simultaneously. A classical computer has to check each possibility one by one. A quantum computer with enough stable qubits can, in a sense, look at many paths at once.
So it offers massive parallelism for a certain problem.
Exactly. This makes them potentially revolutionary for things like simulating complex molecules for drug discovery or materials science problems too complex for a classical simulation. Also, breaking many forms of modern cryptography, which is a major driver for research, both offensive and defensive.
Right, the security implications are huge.
And also solving really complex optimization problems, finding the best solution out of trillions of possibilities, which could impact finance, logistics, supply chain management, things like that. It's still early days. Building stable, large-scale quantum computers is incredibly hard, but the potential is transformative.
Okay, truly mind-bending stuff. Let's come back down to earth a bit, or at least back to the data center. We're generating and moving so much data now. You mentioned that just moving it around is a bottleneck. What's a DPU, a data processing unit, and how does it help?
Right, the data deluge. A data processing unit, or DPU, is a relatively new type of processor specifically designed to tackle that data movement bottleneck within data centers. You can sort of think of it as a highly programmable, very smart network interface card, or NIC.
A smart NIC on steroids?
Kind of, yeah. Its main job is to offload tasks related to networking, storage, and security that would normally bog down the main CPUs.
What kind of tasks are we talking about?
Things like processing network packets going efficiently, handling encryption and decryption of data in transit, managing storage virtualization, running firewalls. Basically, all the complex infrastructure plumbing that takes up valuable CPU cycles in a modern virtualized data center.
So the DPU handles the plumbing, freeing up the main CPU.
Exactly. By offloading these infrastructure tasks to the specialized DPU, the main server CPUs can focus all their power on running the actual applications and workloads they're intended for. It leads to much better overall efficiency, higher throughput, and better resource utilization in the data center. It's about distributing the intelligence needed to manage the infrastructure itself.
That makes a lot of sense. Okay, this focus on efficiency brings us to something you touched on earlier, but let's make it explicit. The environmental cost, the power cost.
Yeah.
Why is performance per watt suddenly the metric everyone's talking about? Why is it arguably the most important benchmark now?
It really has become the crucial metric, and for very compelling reasons. As we've discussed, the sheer growth of computing globally is staggering. Data centers, AI model training, all of this consumes a huge and rapidly growing amount of global electricity.
Right, the energy footprint is massive.
It's massive, and it raises serious sustainability concerns. So energy efficiency isn't just about saving money on the electricity bill anymore, although that's certainly a factor for data center operators. It's become a primary design constraint for all future hardware.
A constraint, not just an optimization.
Absolutely. Whether you're designing chips for a giant data center or for a tiny battery-powered mobile device, the fundamental question is, how much useful computation can you achieve for every single watt of power consumed?
Performance per watt.
Performance per watt. That's the metric driving so many trends we see today. It's why energy-efficient ARM architecture chips are making inroads into data centers. It's why there's such intense development of centralized AI accelerators that are designed for efficiency on specific tasks. It's why CPUs and GPUs have incredibly sophisticated power management features.
So it affects everything from the cloud down to my phone.
Everything. It's the efficiency limit we're constantly pushing against. You could almost call it the new true north for hardware design, balancing performance gains with power realities.
Okay, true north. I like that. Finally, let's talk about where all this amazing, specialized, power-efficient hardware actually lives. We hear about cloud and edge. What's the real difference, and why is this whole edge-to-cloud picture so important now?
Right, the deployment landscape. The future isn't just about massive centralized cloud data centers anymore. It's really evolving into this distributed continuum, stretching all the way from the cloud out to the very edge of the network, close to where data is generated and used.
A continuum. Okay, so the cloud first.
But cloud isn't going away, of course. It remains the best place for large-scale, heavy-duty computation that isn't super sensitive to latency, meaning slight delays are okay. Think training those enormous AI models we talked about, running huge scientific simulations, archiving massive data sets.
Big, non-urgent jobs.
Generally, yes. And the hardware there is optimized for scale, for handling many users at once, multi-tenancy, and, as we just discussed, for performance per watt, because power is a huge operating cost.
Okay, so that's the cloud. What about the edge?
The edge is all about bringing computation and data storage closer to the sources of data generation or the point of action. Why do this? Several key reasons.
Like what?
Low latency is a big one. For applications like autonomous vehicles, industrial robots, or augmented reality, you need near instantaneous processing. Sending data all the way to the cloud and back is just too slow.
Makes sense. Real time requires local processing.
Exactly. Another driver is data privacy and security. Some sensitive data, maybe medical data or proprietary factory data, might need to stay local on-premise rather than being sent to the cloud.
Keeping data local.
Right. And finally, bandwidth conservation. Think of a factory floor with thousands of sensors or a city full of smart cameras. Sending all that raw data to the cloud constantly would consume enormous network bandwidth. It's often more efficient to process the data locally at the edge and only send summaries or critical alerts back to the cloud.
Process locally, send less data.
Precisely. And the hardware at the edge is incredibly diverse because the needs are diverse. It could be powerful servers located in a factory closet, sometimes called the far edge, or tiny ultra-low power AI chips embedded directly into sensors or cameras, the near edge.
So edge hardware is specialized for its location and task.
Very much so. It often needs to be ruggedized for harsh environments, optimized for very low power consumption if it's battery operated, and tailored for specific tasks like AI inference.
So it's not cloud or edge, but cloud and edge.
Absolutely. The future is a hybrid model. Workloads will increasingly be distributed dynamically across this entire continuum. Your smart car uses edge computing for immediate driving decisions, but sends data to the cloud for analysis to improve the entire fleet's performance over time. It's about putting the computation where it makes the most sense for latency, bandwidth, privacy, and cost.
This has been absolutely fascinating, really charting the course for where hardware is headed. Just to wrap things up and tie it all together, how has the end of Moore's Law, this shift we've been discussing, fundamentally reshaped the whole future of computer hardware.
Yeah.
What's the big picture takeaway?
I think the biggest takeaway is that the end of that easy, predictable scaling from Moore's Law hasn't led to stagnation. Quite the opposite. It's kicked off this incredible new era of architectural innovation and diversification. It's arguably more exciting, if more complex.
Forced creativity in a way.
Exactly. We've been forced to get much more creative. We're moving beyond simple, flat, two-dimensional chips towards these intricate modular designs using chiplets and 3D stacking, building outwards and upwards. Future performance gains aren't coming from one magic bullet anymore. They're coming from these heterogeneous systems where a general-purpose CPU acts more like an orchestrator, directing traffic to a whole team of highly specialized accelerators, GPUs, TPUs for AI, maybe even quantum processing units eventually, DPUs for networking.
A whole team of specialists working together.
It's precisely. And underpinning all of this is that relentless focus on energy efficiency, on performance per watt, driven by both mobile needs and planetary sustainability. It's no longer an afterthought. It's a core design principle. And finally, all this diverse hardware won't just live in the cloud. It will be deployed across that entire distributed continuum, from massive data centers right down to intelligent sensors at the very edge. So, yeah, the end of Moore's Law hasn't been an endpoint, it's been a turning point, launching us onto this thrilling, branching journey towards a future filled with unprecedented specialization, efficiency, and ultimately computational power we're only beginning to harness. It's truly a renaissance period for hardware design.
A renaissance in hardware design. That's a fantastic way to put it.
Yeah.
Thank you so much for walking us through all of that. It's been incredibly insightful and has really clarified the landscape.
It was my pleasure. Glad I could help unpack some of it.
And to you, our listeners, thank you for joining us on this deep dive into the future of computing hardware. I hope you found it as illuminating as I did. Be sure to join us for our next deep dive, where we'll be shifting gears a bit to explore cybersecurity fundamentals, principles, practices, and defenses. Should be another crucial topic. And please be sure to subscribe to our channel, Tech AI and Beyond, so you don't miss any of our upcoming deep dives into the technologies that are shaping our world. Until next time, keep exploring and keep learning.